Hello, my name is Monica and we're Group 29. Today we'll be presenting our automatic Sudoku solver. The link to our GitHub and YouTube is attached and can be accessed by clicking on the icons. So first, our problem statement focuses on a core challenge and three objectives. The challenge is to develop a solver that can not only solve the puzzle but also recognize it directly from an image. To achieve this, we broke it down into three objectives. First, digit recognition to read the pre-filled numbers from uploaded images. Second, puzzle solving using optimized algorithms. And finally, solution display for a complete solved puzzle.
My name is Jasmine, and for this slide, we will talk about our project scope and comparative evaluations. So this slide shows the overall scope of our project. So basically, we will test different algorithms to see which one can solve the Sudoku puzzle the fastest and the most accurately. Next, we will perform a different analysis across different difficulty levels, including the easy, medium, and hard puzzle, to understand how each algorithm performs under different conditions. At the same time, we will also evaluate the two image recognition methods for digital extractions to find out which method can best recognize the number from a Sudoku image. Then, we did a performance analysis of their digit accuracy, comparing how often each method correctly identifies the pictures. Finally, we will combine the best performing solving algorithm with the most accurate image recognition method to build one efficient and reliable Sudoku solver. So in the comparative evaluation, first, we will talk about the phase one, which is Sudoku algorithm comparison process. So for each algorithm, we will run the Python command. They're able to run these three TST at the same time, and is able to generate the CSV log after we running our algorithm. So it's able to help us to compare every algorithm efficiently. So the next slide, we will talk about the Sudoku puzzle digit detection process. Then we will input the picture and use the two image recognition method, which is the CNN and the tesseract or CR, to detect the image, and later compare both methods based on the accuracy. For now on, I will pass to my next member.
My name is Liao Chi Kwang. Before we start the comparison, let me introduce a convolutions neural network for you. It's a kind of deep learning models that can actually learn to see instead of us to telling it what is the edge or a shape looks like. The network figure out by itself, it learns the special features, things like line, corner, or patterns directly. So this is the CNN architecture. You can take a look at the input part. So we are using 28 by 28 by 1s. The reason we use the channel 1s is because we are not using the colors. We are using the MNIST dataset provides the grayscale digits. And also we are using the max pooling in this part. So the max pooling, we keep the strongest features in the regions, and the average pooling will keep some of the noise inside. In the algorithm part, we have trained our models, the CNN models, by the step 1, the forward pass to perform the convolutions, compute the output predictions. And then it will pass through the feature mat. The loss function will measure how well is the model performs, and the loss function compare the prediction probability vector from the previous step, which is the step 1. And then for the step 3, the back propagations is also known as the backward pass. It is the process that let the CNN learns from mistake by calculating the gradients and update the weights. This cycle forward pass, loss calculation, and back propagations repeat many times across 1,000 of the image, allowing the models to gradually improve and become more accurate. We set the number of the epoch to 15 because we wanted a balance between the learning perform. It will, if we are set few epoch, the models will have not enough times to learn the complex pattern. But if we have too much of it, the model might start to overfit, meaning it will memorize the training data instead of generalizing to new image.
Hello, my name is Jessica. Here is the short introduction to Tesseract OCR. Tesseract is an OCR engine. It reads text for image and recovers it to the editable text. In our project, we use it to recognize the digit for the pseudocode image. And Tesseract work in two spaces. First one is we reprocess the image, detect the pseudocode grade, and crop into 81 cells, cover to the gray cell, and remove the noises. And second is Tesseract analyze each cells and try to match the digit basis on the predefined character shapes. We compared the Tesseract with our CNN models. Tesseract takes 10.84 seconds, while our CNN finish in 0.26 seconds, around the 40 times faster. Tesseract reached 65 accuracy, while CNN achieved 100 accuracy. Tesseract cannot learn, but CNN can be trained with more data and keep improving. However, the Tesseract is rule-based, so it's very sensitive to noises, thin and handwriting, and grid lines. Because of this, its accuracy will unstable and cross the difference image. So the CNN is faster, more accuracy, and more scalable, and making it better choice and for pseudocode digit and recognitions. 如何呢？
So the first algorithm that we use is the basic backtracking algorithm. This pseudocode solving algorithm uses a brute force backtracking approach. It has three main functions. The first is the pseudo setup function. It builds the grid structure, defining rows, columns, and 3x3 units so that the solver knows which cells are connected. The next function is the pseudo validate function. It checks whether the current grid is valid and complete. Now the core part of the function is the pseudo brute force function. So how does this algorithm work? This is the core recursive backtracking. So if pseudo validate returns true, we're done, it's success. Otherwise, we pick the first empty square. We compute the set of possible digits for that square by excluding any digits already present among its peers. If there are no possibilities, we increment the backtrack's counter and return false to backtrack. Otherwise, we loop through each candidate digit, increment nodes, place the digit, and recursively call pseudo brute force again. If a recursive call returns true, we propagate success. If all candidates fail, we undo the assignment, increment, backtracks, and return false. As you can see from the slides, this is the image of our main function, which is the pseudo brute force function.
So the second algorithm we are using are forward checking, backtracking, and MRV to solve the pseudocode. First, we need to run the forward checking function and use the set domain inside the forward checking to create the possible numbers from 1 to 9 for each empty cell's domain. Then, the algorithm will look through every cell in the bot and set the domain to -1 if the cell already filled with the number. Then, it will check its neighbor cell with the same row, same column, and 3x3 bot and remove that number from their possible domain. This process made the solving faster. After that, it will call the forward checking recursive function and use the MRV to find the cells with the smallest number in the domain. So once the algorithm finds the cells with the smaller domain, then it will select one of the numbers and check if it is valid and run forward check it again to prompt its neighbor domain. This process will continue recursively, and if the algorithm finds that the cell has not any valid numbers to fill, then it will do the backtrack and try a different number instead. And the process will continue until the pseudocode is solved.
Hi guys, I'm Jiasheng, and I will be presenting the hybrid approach which combines four algorithms. Since my teammates has already explained heuristic, forward checking, and backtracking, I will focus on the remaining component AC3, which stands for arc consistency algorithm. AC3 works by propagating constraint to all related cells, though in the same row, column, and subgrid. It prunes impossible value before guessing begins, helping the solver achieve global consistency early. For example, if a cell already contains the number 5, AC3 automatically removes 5 from the domains of all related cells in that row, column, and subgrid. This step reduces the search rate significantly and makes the solving process faster. The hybrid Sudoku solver starts with AC3, which prunes impossible value based on Sudoku rules. If AC3 doesn't completely solve the puzzle, the solver moves to a search phrase guided by heuristic. The minimum constraint variable heuristic Select the cell with the fewest possible value to minimize the branching, while the least constraining value heuristic pick the value that caused the least restriction on the neighboring cell. Each time a value assigned, forward checking remove it from related cell domain to prevent conflict. If a contradiction occurs, backtracking undoes the previous assignment and try alternative value. The hybrid workflow combining AC3 heuristic forward checking and backtracking merge logical inference with guided search, ensuring the solver find a solution efficiently even for complex Sudoku puzzle.
First, in the initial board setup, the algorithm keeps the given number and fills the empty cells randomly, so each row already has all digits from 1 to 9. That means it only needs to fix column and box conflicts later. Second, the conflict detection function counts how many times a value breaks Sudoku rules by checking in the same row, column, and the 3x3 box. Next, the min-solver loop keeps finding conflicted cells. It picks one, tries swapping it with another cell in the same row, and keeps the swap and reduces conflicts the most. If no swap helps, it assigns the least conflicting value. Finally, the row-based swapping strategy keeps each row valid, while fixing column and box errors. If swapping fails, the algorithm simply assigns the best possible value.
Next, I would like to share and talk about our insights. We'll be sharing the results from our comparisons and be using graph for better visualization. To compare our four algorithms, we are using the following metrics. First, the runtime. It measures how fast our solver runs, showing its efficiency. Next, memory. It tracks the peak RAM usage to see how space efficient it is. Next is node. It counts all unique states the solver explores. Fewer nodes will mean smarter searching. Next, backtrack. It tells us how often the solver has to undo decisions. More backtrack would mean the puzzle is harder or the algorithm is less efficient. And accuracy, it shows the percentage of puzzles being solved correctly. And lastly, we have timeout. It checks if if solving takes longer than 30 seconds, highlighting the puzzles that challenges the algorithm. These are the results from running all four algorithms. So for better visualization, we'll be inserting graphs instead. So from this graph, this is a runtime analysis graph. We can see that the third algorithm, which is a hybrid approach of AC3 and heuristics plus forward tracking and backtracking, this achieved the highest success rate and the shortest average runtime across all difficulty levels. This proved that combining constraint propagation AC3 with smart search heuristic is far more efficient than using plain backtracking or local search alone. Okay, so the next part we'd like to demo our fully functional program. So the first part that we do is over here is the combined program for our CNN and our algorithm, and the next part is the external image. So for this, we have to import an external image for us to run. For this example, our team member took a photo on their mobile device and imported this image into our program. And next, this is the combined folder. So to run this, we have to go to README file, and there is a session where we wrote about how to run this combined folder. So all you have to do is copy this Python code and we paste it here. So an explanation of this code would be the first part is our Python folder, and the next part is the image that we will be running. So all you do is click enter. And over here, as you can see, this is the original image that we imported, and the second part is the digits that the CNN model detected. And lastly, we have this solved Sudoku puzzle, and this Sudoku puzzle is solved using our third algorithm, which is the AC3 plus backtracking algorithm.